Welcome back, everyone. Keith Kearnes is going to talk about relative Maltsev definability. Please, Keith.
Yes, okay. So the title I posted to the webpage was Relative Maltsev Definability, but it's about a paper I wrote earlier this year about relative Maltsev definability of some commutator properties. You'll see this is a little bit of a pretentious title, but I'm going to use it. So let me start by telling you why I care and just give you a brief 1 or 2 line idea about the whole talk. Here's the problem. Which varieties have commutative commutator? Okay. Now I'm using the term condition commutator, which is not commutative in every variety, but it's commutative in a lot of varieties, such as congruence modular varieties. And if I give you a finite algebra and ask if the variety it generates has commutative commutator, how would you decide that answer? Okay, here's what I know. I don't know the answer to the question, first of all. I don't know which varieties have commutative commutator, but I know this class of varieties is not Maltsev definable. But if you restrict to the class of varieties that have a Taylor term, then the class becomes Maltsev definable. Okay, a Taylor term is an idempotent term that defines the weakest idempotent Maltsev condition. So it's a very weak underlying structure that involves idempotent terms. And if you impose one, we can think of that as a weak condition that you're imposing, but it eliminates some pathological behavior. And if you restrict to just those varieties, then the varieties with a commutative commutator that have a Taylor term, that class is definable by a Maltsev condition. So here's the theorem, which models everything. It's a model for everything I'm going to say today, that this is a statement about varieties. And the theorem is, first, the commutator is commutative. And I'm talking about the term condition, the commutator given by the current term condition. If that's true, and the variety has a Taylor term, that's equivalent to saying the variety has a difference term. And there is a Maltsev condition that defines the class of varieties with the difference term. So the class of commutative varieties with the commutative commutator is not Maltsev definable, but if you have Taylor term as well, that class is Maltsev definable. So here's what I mean about relative Maltsev definability. It's a theorem of this structure where you have a property that you're interested in, and you have a weak ground Maltsev condition, gamma. Gamma is for ground. And throughout this talk, it's always going to be there exists a Taylor term. And I'm interested in whether the property plus Taylor term is a Maltsev definable property. If there's some Maltsev condition sigma, which defines the same class of varieties as those that have P and have gamma. Why? Why do we do things like this? Well, I just wanted to give a very quick statement. First, for non-specialists, I think everyone can appreciate this type of answer. Suppose you want to prove a theorem, and you know you're going to need an idempotent Maltsev condition somewhere, and the weakest such condition is Taylor term. So let's say you know you're going to need a Taylor term somewhere in your argument, but the method of argument uses commutative commutator throughout the proof, some property like P. What hypothesis do you need to state to make the proof work? And if you have P plus gamma is sigma, then the hypothesis sigma will be the most general assumption that gives you both. So this type of theorem, P plus gamma is sigma, is useful if you want to optimize the assumptions on your proof. Okay, I think anybody can appreciate that, whatever P and gamma and sigma mean. I got involved in this because I was interested in Park's conjecture. Ross Willard and Agnes Sendre and I proved Park's conjecture for varieties with the difference term. Typo here, term appears twice. Okay, we proved it for varieties with the difference term. We started out our work trying to prove it for varieties with the Taylor term. We actually thought we had proved it in that setting, and then we found some problems. So when we wrote the paper, we wrote it in a more restricted setting, that of a difference term. And because we knew we had a difference term, we freely used commutativity of the commutator throughout our argument when we wrote up the paper. This is the statement of Park's conjecture. A finitely generative variety with a finite residual bound is finitely based. We still don't know if this is true in general, or even if it's true with the Taylor term. We have a proof with the difference term. And the proof uses properties of the TC commutator. That's why I keep emphasizing I want to talk about the TC commutator, because there are constructions that are involved there that use things like centralizers that wouldn't exist for other commutators. So not all commutators have centralizers associated with them. So we need the TC commutator, and we want to know how properties of the TC commutator move from constructions of large subdirectly reducibles and translate into the commutator arithmetic given by the Fries-Mackenzie property C1. I won't tell you what C1 is, but if you've read the Fries-Mackenzie commutator theory book, you know they have it in there. And also they wrote an earlier paper where they introduced C1 in the early 80s. So this is specifically what we were interested in. We were interested in proving Park's conjecture in the greatest possible generality. Our proof uses commutative commutator. It uses non-trivial idempotent Maltsev condition. We were hoping we could prove it for Taylor varieties, but really we needed commutative commutator to talk about C1 properly. We still haven't figured out what is the right way to express C1 if you don't have commutative commutator. And that's why our paper ended up being phrased in the language of difference term. So I want to understand commutator arithmetic for varieties that have a Taylor term but don't have a difference term. Okay, so let's start the talk now. That's just why we're doing the talk. Let's go ahead and do the talk. I'm going to say things which I think are review for some people. What is a Maltsev condition, for example? A strong Maltsev condition is a positive primitive sentence. Positive primitive means it has the structure existential quantification, conjunction of atomic, and this is in the language of clones. This is an algebraic language. So atomic means equations. So there exists some elements where there's some conjunction of equations satisfied involving those elements. And here's an example. Okay. There exists a clone element, T. This is going to represent a 6-variable term. There exists a clone element. That's the existential part. And then conjunction of atomic. So there's a sequence of equations that must be satisfied. First, T of x is x. This is idempotence of T. And this is really two equations. First equals second and first equals third. I just wrote them all out because they're all equal. But the important thing here is just the pattern of x's and y's. So this is an example of a positive primitive clone sentence. There exist clone elements satisfying some equations. A variety satisfies it if the clone of the variety contains an element T realizing the indicated elements. Now, what I mean here, first of all, the clone of a variety, a single element of the clone is really an equivalence class of terms. And I really mean pick one of the terms in the equivalence class, and I want these identities to be satisfied. If you pick a different one from the same equivalence class, if two terms come from the same equivalence class and one of them realizes these identities, so will the other. But really, an element of a clone is an equivalence class of terms, but I'm going to just treat them as if they were terms. And when I say that the identities are realized in V, I mean V satisfies these identities. So there is a term in the language of V where these identities are satisfied. That's what it means for a variety to satisfy sigma. And once you know what it means for an object to satisfy a sentence, you can talk about the sentence defining a class. It defines the class of those things which satisfy the sentence. That's strong Maltsev condition. And this is called Olszak's Maltsev condition. I really want to talk about Taylor terms today. Let me get to the foot of the slide before I tell you why I mention Olszak's condition instead of Taylor's. So what is it? This is strong. This is ordinary. At the foot of the slide, we have ordinary Maltsev condition. It's a sequence of strong Maltsev conditions. As you go through the sequence, they get successively weaker. So the nth strong Maltsev condition implies the n+1 strong Maltsev condition. A variety satisfies capital sigma if it satisfies little sigma n for some n, and capital sigma defines the class of the varieties which satisfy it. Okay. Now, Taylor found the weakest idempotent Maltsev condition, and he presented it as an ordinary Maltsev condition. So it's an infinite sequence of successively weaker, strong Maltsev conditions. This happened in the 70s. Just a few years ago, I think it was 2018, maybe, Olshak found that Taylor's ordinary Maltsev condition is equivalent to a strong Maltsev condition, and that's the one that I've written down here. So any variety that satisfies Taylor's Maltsev condition also satisfies Olshak's, and conversely. And now I can just write it down. You can see it. Rather than telling you an infinite sequence of weaker and weaker things, I can just write down Olshak's condition. But when I talk about a Taylor variety, I mean it has this Olshak term, 6-variable term. It's idempotent, and it satisfies these pattern of identities. Okay, now that's Maltsev definability in logical or model theoretic sense. We're talking about algebraic objects satisfying identities. We can say the same thing in a categorical way. So this is how you do it categorically. I'm going to define the Olshak variety to be the variety that has finite presentation associated to the Olshak sentence. Let me just go back and look at the Olshak sentence one more time. So this is the previous slide. I'm saying there exists a T and finitely many equations involving T. Now, I'm going to rewrite that as a presentation relative to the class of all varieties or class of all clones. This is a presentation, generators and relations. I'm going to look at a variety which has language, just one non-logical symbol, which is T, representing a 6-variable function. And the equations for the variety will be the Olshak equations. So this is a presentation of a variety. Okay. Now, the class of all clones of varieties is a variety itself of multi-sorted algebras. And we can talk about the universal property of presentations. That is, a homomorphism from the clone of the Olshak variety to the clone of another variety is completely determined by specifying where T goes. And T has to map to an element of the clone of V, which satisfies the relations. So a morphism from the clone of Olshak's variety to an arbitrary clone of a variety just picks out a T satisfying the equation. So it says that the clone of V satisfies the Olshak sentence. It has a T satisfying these identities if there is a morphism, or if and only if there's a morphism. So I can talk about satisfaction of a sentence in terms of these maps. Maps can be composed. If you look at composition of maps in any category, they pre-order the category. I will write O is less or equal V. If there's a map from O to V, that's a pre-order on the category of varieties. And if I have, let's say, a morphism from U to V, I say U is interpretable in V. Or I'm not the only one who says that. I guess people have been saying that for decades now. Good example to keep in mind, groups are interpretable in rings. I think of groups as having a multiplication, an inverse, and an identity element. And I can take a clone map that takes the multiplication to ring addition, the inverse to ring negation, and the identity of groups to the additive identity of rings. That gives me a morphism from groups to rings, and it's showing me that a ring has an underlying group structure. It has underlying additive group structure. That's what it means to have a morphism between varieties, that the variety on the right has underlying structure that comes from the variety on the left. So that's what less or equal means. As I said, it's a pre-order. Every pre-order has an associated equivalence relation. Two varieties are equivalent if they are mutually interpretable or bi-interpretable. I guess the best known example of this is Boolean algebras and Boolean rings. Every Boolean algebra can be thought of as a Boolean ring. Every Boolean ring can be thought of as a Boolean algebra. They're bi-interpretable, so we say they're equivalent. I'm going to put square brackets to indicate equivalence class. So they're equivalent if their equivalence classes are equal. And we can order equivalence classes by just ordering a representative of each class. If you have two equivalence classes, I'll say the first equivalence class is less or equal to second. If some representative of the first is less or equal some representative of the second, that's well defined. This is just, I guess, like second year discrete math, that preorders have associated equivalence relation, and if you factor by it, you get a partial order. Now, if this came from the category of clones or category of varieties, in general, if a category has products and coproducts, then this poset will have joins and meets, and it will be a lattice. And that is the case here. The interpretability relation is a lattice order on bi-interpretability classes of varieties. So that gives us a visual way to think about Maltsev conditions. Let me draw this picture. So this big blob is the lattice of interpretability types. All the dots represent a square brackets of a variety. And the Olshak variety is a finitely presented variety. So I picked a finitely presented variety, and I'm interested in everything you can interpret it into. That means everything that's above it in the order. That's a principal filter. So a strong Maltsev filter is a principal filter in this lattice, where the representative of the principal generator, there's one representative at least that's finitely presented. So a strong Maltsev filter is a principal filter in this lattice where the representative is finitely presented. Okay. And you can show that lattices have an Olshak term, groups have an Olshak term, rings have an Olshak term. So they're all in this filter, the Olshak filter. And I put rings above groups because we saw that groups interpret into rings. And I put rings, groups are not above lattices. Yeah, lattices are not interpretable into groups. Okay. Now that's strong. What about ordinary? So remember, ordinary Maltsev conditions were an infinite sequence of successively weaker strong Maltsev conditions. If I pick a strong Maltsev condition, I'm looking above one of these dots, and the generator should be finitely presented as a variety. So this class has a generator that's a finitely presented variety. I'm interested in this class and everything above it. That's defined by the strong Maltsev condition represented by Q0. And now here's a weaker one, so it gives me a bigger filter, and a weaker one gives me a bigger filter, and I take the union of all of those filters. That's a Maltsev filter. Okay, so that's what I mean when I talk about Maltsev definability. But today's talk is about relative Maltsev definability. And so I'm interested in properties, for example, commutativity of the commutator, where if I collect all the varieties with commutative commutator, it is not a Maltsev definable class of varieties. But if you restrict to the Taylor filter, then they become Maltsev definable. This is what that looks like in a picture. So Taylor filter and Olshak filter are the same. We now know, because of Olshak's paper, that it's a principal filter generated by a finitely presented variety. Where are the varieties that have commutative commutator? There. They look like this. That is, there are lots of them. Lots of varieties have commutative commutator. But I've indicated in red what it means to have commutative commutator. There's this line. I'm defining some filter, but I'm indicating that there are things outside the filter that, in fact, the class of varieties do not represent a filter. And I even changed my color from red to pink, because there are classes where two varieties represent the same class, and one of the varieties has commutative commutator and the other does not have commutative commutator. So I can't really assign a color to that interpretability type. because there's not a well-defined assignment. It's not true that all the varieties in the class have the property of commutative commutator. Some do, some don't. So I gave it pink. And the easiest one to see is the bottom element. It's easy to see that the variety of sets has commutative commutator and the variety of semigroups does not have commutative commutator, and they both have the same interpretability type. Okay, that's the easiest one to see. So I have some picture like this. And one of the things this means is if you just hand me a finite algebra and ask me, does it generate a variety of commutative commutator? I have no way of figuring that out. If I knew it was associated with the Maltsev condition, I could plug it into a program and run the program and determine if that Maltsev condition is satisfied. But if it's not defined in a nice way, I don't even know how to check. Every instance of that problem is you have to develop your tools for that instance. Okay, so that's the picture for relative Maltsev definability. You can do this in lots of settings, although for this talk, I'm always doing proving theorems relative to this Taylor filter or Olshop filter. That is, I'm interested in properties that are not Maltsev definable, but if you intersect the class of the interpretability types of varieties that have the property with the Olshop filter, the intersection will be a Maltsev filter. Okay, and commutative commutator has that property. It turns out that if you look at the varieties that have commutative commutator and interpret O, you will get a Maltsev filter. It won't be a strong Maltsev filter, but you will get a Maltsev filter when you intersect those. Okay, so that's the idea of relative Maltsev definability. And for those who need a reminder about the TC commutator, I just have a couple slides of definitions. I'm interested in a commutator operation defined by the term condition. There are three main definitions you have to see. One is alpha beta matrices. Here, alpha and beta are congruences on an algebra. So I start with an algebra, I pick two congruences, and then I construct the alpha beta matrices. They're all the matrices you can construct where you take a term operation of the algebra, you divide its variables into two blocks, and on the first row, I pick elements. In the first block, they're the same elements, but in the second block, they need not be the same. And then when I move to the second row, I can change my first block elements, but I don't alter my second block elements. I form all these matrices, and that's the set of alpha beta matrices. Okay. If you have never seen it before, you won't learn it from what I say here, except to say that if you follow through this with groups, you will end up with a group commutator. Centralizer relation. The centralizer relation, we say alpha centralizes beta modulo delta if when the first row elements are delta related, it implies the second row elements are delta related. So for any alpha beta matrix, delta on the first row implies delta on the second row. And I write alpha centralizes beta modulo delta this way. Okay. Then last definition.
To be alpha related.
Okay. Yeah, I don't, because my slides are up, I don't see if somebody puts their hand up. So just speak out loud if you want to interrupt me. Is there a question?
Oh, you forgot to mention alpha and beta in the alpha beta matrices. I think. You know, the change has to be alpha related. And
Yeah,
beta related.
it's hidden on this last line right here at the end.
Okay, I take that back.
I think I didn't say it. I didn't say it, but I wrote it. Yeah, okay.
Okay, good.
Yeah, okay. The commutator is of alpha and beta, congruence is alpha and beta, is the least delta which makes this relation true. And the only thing I have to say is, if you already know this, you didn't need to hear it from me, but if you don't know it, you didn't learn it from me either. But the remark I'll make is this. In groups, you define the commutator with the commutator word. And we're trying to find a language independent way of defining the commutator. It turns out to be easier to define the centralizer. And for groups, what we're thinking of when we define the centralizer is this ternary relation. alpha commutator beta gets below delta. We're thinking of that ternary relation. Now, if you can define that ternary relation, you can define the commutator. You just define it as the least delta, which makes this inequality true. The least delta will be equal to what's on the left. Okay, and that's how we define the commutator. So we're trying to define C alpha beta delta as if it meant this. And for groups, it does mean this. For any algebra, we have a forward implication. For groups, we also have the back implication. So for groups, this centralizer information is exactly the same as this, and it's exactly what you need to define the commutator. That's why the centralizer comes into the theory. But when you move away from groups, you lose one of these implications. So there's more information in the centralizer than there is in the commutator. Okay, so that's all the review. Here are the commutator properties that are the subject of this talk. Okay, so all of these properties are true for groups, and all of these properties fail for semigroups. Okay. Commutative commutator. Groups have commutative commutator, semigroups do not. The left distributive law. Here I'm joining, this plus means join of congruences, and I'm saying the commutator distributes over the join in its left variable. That's true for groups, false for semigroups. Right distributivity. We have to consider them both because the commutator may not be commutative. For groups, it's right distributive. For semigroups, it need not be. Semi-distributive. If X commutators Y and Z to the same place, then it also commutators that are joined to that place. True for groups, false for semigroups. Right annihilators exist. You take a congruence delta below a congruence theta. Is there a largest X that I can put in here so that theta centralizes X modulo delta? If I swap the order of theta and X, there will be a largest. The left centralizer exists. That follows from the definition. The definition does not give us that right centralizers exist. The centralizer is symmetric in its first two variables, true for groups, false for semigroups. The centralizer is defined by the commutator. So remember, we invented the centralizer, or not we, but let's join in with those people who invented it. This centralizer was defined to allow us to define the commutator by this relation, but that it turns out they're not equivalent to each other. We just have the forward implication, but we have the backward implication for groups. We don't have the backward implication for semigroups. The centralizer is stable under lifting in its third variable. If CXYZ holds and you enlarge the Z to Z prime, CXYZ prime will still hold. Now that's true of this ternary relation in the previous line. If X commutator Y is below Z and Z is below Z prime, transitivity will tell you that X commutator Y is below Z prime. So that is true of this relation, but it need not be true of the centralizer relation. This is true for groups, false for semigroups. Now you may ask, what if I want to lift the Z a little bit, not too much? I want to keep it below X and Y, but I want to allow myself to lift it a little bit. Then I say weakly stable in its third variable. Okay, so those are a lot of properties. They're all true for groups. They're all false for semigroups. None of the properties that I've listed are Maltsev definable properties. That means if you look at the varieties that satisfy one of those bullet points, the class you get will not be definable by a Maltsev condition. And it's an easy argument because the variety of sets. If you work through the definitions of the variety of sets, you will find if A is a set and alpha, beta, and delta are congruences, it just means they're equivalence relations, then C alpha, beta, delta always holds for whatever choice of alpha, beta, and delta you have. And therefore, alpha commutator beta is 0, whatever alpha and beta are. So these are trivial, the centralizer is a kind of trivial relation. It holds for all triples. And the commutator is a trivial operation. It's the constant zero function. And therefore, it satisfies all of those commutator properties. You can check all of those properties hold for these trivial things, or you can just believe me when I said it's true for groups, then abelian groups. It's true for all abelian groups, and abelian groups also have the property that these are trivial. The commutator of two normal subgroups in an abelian group is always 0, and the centralizer holds for all triples. So if it holds there, it's got to hold whenever these are trivial relations. Okay. So sets satisfy them all. If one of those properties was Maltsev definable, sets would satisfy the Maltsev condition. So the entire filter above the variety of sets would be the Maltsev filter that's associated, but sets are at the bottom of the lattice. The entire filter is the whole lattice. So if sets satisfy that Maltsev condition, then every variety satisfies the Maltsev condition. And that's not true because semigroups fail all of those properties that I listed. So it's easy to see that none of the properties listed is a Maltsev definable property. Okay, but they're all relatively Maltsev definable. And I have two theorems that I want to present. First theorem is, so we're always working with respect to Taylor varieties. We always assume we have a Taylor term or Olshak term in our variety. Then all of those properties become Maltsev definable. Some of the properties are equivalent to congruence modular varieties. That is, let me just put the whole slide up. So here are 6 of those properties. If you have a Taylor term and your commutator is left distributive, that's item number 2, then your congruence modular. And conversely, if your congruence modular, the commutator will be left distributive. These are equivalent. All of these are equivalent on this list. And the class of congruence modular varieties is Maltsev definable. Alan Day showed that in his thesis, his master's thesis. He gave a Maltsev condition that defines the class of congruence modular varieties. So this is a Maltsev class, but Taylor term plus any of these other 5 give you the same class of varieties. Left distributivity, right distributivity, centralizer symmetric in its first 2 variables. It's stable under lifting in its 3rd variable. Centralizer is defined by the commutator. Any one of these is equivalent to congruence modularity if you have a Taylor term. That's the first theorem. And the second theorem that I want to give, let me just put it all up. Oops, there we go. Difference term. I'm not going to tell you what a difference term is. I'm just going to say that there is something that's introduced by Goom, difference term. And there is a Maltsev condition which defines the class of varieties with the difference term. And we know in these varieties that they all have a Taylor term. We know that the Maltsev condition for difference term is a non-trivial idempotent Maltsev condition, and Taylor term is the weakest non-trivial idempotent Maltsev condition. So they all have a Taylor term. And any one of these properties together with the Taylor term characterizes what it means to have a difference term. Commutativity of the commutator, right semi-distributivity of the commutator, right annihilators exist, centralizer is weakly stable under lifting in its 3rd variable. Okay, now I'm not going to tell you anything about how to prove these things. A few of them are hard, but then you can see that some of these are related to each other. Once you get the hard ones out of the way, the others are not very hard to prove. What I'd like to do instead is put in a plug for UA Calc. This is some software online that Ralph Fries and Emil Kish and Matt Valeriat helped to develop. And I want to show how we could use this to decide if a variety has commutative commutator. So that property is not a Maltsev definable property. That means it's not obvious how you would check if a variety has a Taylor term, but has commutative commutator. But if you know your variety has a Taylor term, then there's a test. You just test for a difference term. So I want to show you how I would do the test. I have some time, don't I, Peter? I think I still have some time to do some calculations.
For sure, yeah.
Okay, good. So I've never done this before, but I would like to share a copy of UA Calc in my window and do calculations while you're watching. I remember the first time I used this, I just thought it was magic, that you could prove theorems by just plugging numbers into this program. Okay, so you all see a copy of UA Calc, and I'm going to add the 2-element group. Okay, the 2-element group, I'm going to input it. So I click on the file. I want to build a new algebra. So I want to say it's new. Now you don't see this because a second window just opened up, but it's giving me the option to put the name in. I'm going to call this Z2. Okay, so that's the name I give it. It asks me in a separate window, what is the cardinality? I'm going to tell it cardinality 2. So I plug in a 2, and now it's there. You can see at the bottom line, this blue line that appeared, A0, name Z2. It's a basic algebra. It has 2 elements, but I haven't told it what its operation is. The elements it's telling me in the element key table are 0 and 1. I want to add a multiplication. So I clicked on add. You didn't see a new window open up because Zoom is not showing you my second window, but I'm going to call it operation star. And then what is its arity? 2. I tell it, and it gives me the option of filling out a binary table on the element 0, 1. And I want to put in the 2-element group. And it's your turn to correct me if I get that wrong. That's what I believe is the correct operation table for the 2-element group. That's my operation A0. Okay. And there's a lot of things you can do, like check what is its congruence lattice. It's simple, right? It's a simple lattice, a simple algebra of size 2. This is what its lattice looks like. But what I care about are Maltsev conditions. I'm interested in whether it has commutative commutator, and the theorems we just have only work if you know you have a Taylor term. So I click on Maltsev and look for Taylor term. It's right here. And it says there's a faster algorithm here. Weak 3 edge term is fast. I do the calculation. You see what just happened. It found a Taylor term in 150 milliseconds. Okay, and it gives some citations on what those things mean. So we are in the context when we deal with the 2-element group. We know it has a Taylor term. So if we want to know what the variety generated by the 2-element group has commutative commutator, the theorem says that's true if and only if you have a difference term. So I want to go and look for a difference term. And now it found a difference term in 18 milliseconds. And so it has one. And so it tells me the commutator is commutative. Okay, that's not a surprise, right? It's an abelian group. All groups in the variety are abelian. That's the commutator is always 0. That's a commutative operation. It's not a surprising thing. I'm going to now put in a second algebra. This is going to be the 2-element semilattice. I'm going to call it S2. And I'm going to tell the program the cardinality is 2. And I'm going to add an operation. I want it to be the same signature. So I'm going to call it star is the operation. And it's a binary. I will tell it. So now I want to put the 2-element meet semilattice in 0, 0, 0, and 1. Okay. And you can check what its congruence lattice looks like. It looks just like the other one, except the other one was yellow and this one is black. And that's information from tame congruence theory associated to these algebras. Yellow means type 2 and black means type 5. Okay, so that's useful. Let's do the same calculations here. Does the 2-element semilattice generate a variety with the Taylor term? It found one in 25 milliseconds. You look in this dialog box and you'll see it found a Taylor term in 25 milliseconds. What about difference term? It found one in 18 milliseconds. So the variety of semilattices has commutative commutator. That's also not a surprise if you're familiar, but now I want to take the product. I want to take the variety generated by both of them. And I go to tasks. No, I don't. I go to HSP. HSP allows me to take products. I'm going to take a product. Another window open asking me how many factors. I want 2 factors. Choose the first factor. I choose the group as my first factor to the power 1. And then for the second factor, I choose the semilattice. And I do that to the power 1. And I get a product. And if you look here at the algebras, A2 is a product of Z2 and S2. If I go back to the editor, it's got a 4-element table. It's a product of 2 2-element algebras, so it's a 4-element algebra. That's what the table looks like. Let's check the Maltsev condition. Does it have a Taylor term? Yes, it found a Taylor term for the variety generated by the 2-element group and the 2-element semilattice. It found it in 16 milliseconds. Okay. Does it have a difference term? No difference term. It says there is no difference term. It found out in 34 milliseconds. If it had a difference term, there's a place to search. You examine the free algebra on 3 generators in this variety. You look for it. You have to check if certain equations hold. It studied them all, checked the equations. They don't hold. So it doesn't have one. And that tells us that although the 2-element group generates a variety with commutative commutator, when you think of the 2-element group as a semigroup.
Using
And
my
the-
calculator.
Say it again, Ralph.
Oh. Nothing. My
All right.
wife's looking at this picture here. That's
Familiar
fine.
to her. It's familiar. Yeah. So the 2-element group generates a variety with commutative commutator. The 2-element semilattice generates a variety with commutative commutator. I'm thinking of them both as semigroups. Algebra is one binary operation. If you generate a variety with both of them, that's the same as generating a variety with their product. The variety does not have commutative commutator because it has a Taylor term and doesn't have a difference term. Okay, so it does give us a way of testing if a variety has commutative commutator under the assumption that the variety has a Taylor term. Okay, so this is just my pitch for UA Calc, which I think is a magical tool, and I use it whenever I can. Ralph may be able to correct me when I said how it looks for a difference term. I said it, Ralph, I said it goes to the free algebra on 3 generators. There's a finite number of terms that represent the elements, and then it checks if certain equalities hold and decides if there's a difference term. Is that what you're doing? For Taylor term?
Yes, that's essentially what it's doing. Yeah.
All right. Okay, so that's all I wanted to say. I might have a couple of minutes left. I guess we have time now. Peter will take over as moderator. And while I'm sitting here, maybe I will just share a picture of, yeah, I want to share this picture. PALS, yes. I want to share the fact that PALS still has some opening slots this semester. If somebody wants to present a talk, there are still some open slots. Let me move it up a little bit. You can see we have some slots. So Peter, I'm turning it over to you now.
All right. Well, thanks, Keith. For the nice talk. Do we have any questions? Comments?
I do.